Hello. Let us try to understand today biasing of a general purpose transistor. We have taken for the purpose a transistor 2N3903 or 3904. It's an NPN silicon transistor. The data sheet gives like this: the voltage parameters and current parameters and so on. The most important thing that perhaps which we would like to be concentrating on is the gain factor of this. What we find, the gain is roughly 50 to 100 depending on the type, and at about 1 kilohertz with about 10 volt DC, and current of about 1 milliampere as far as the small signal current gain is concerned. So we'll be confining to these parameters for designing the biasing for a RC coupled amplifier. And the other parameters like the package is TO92, which is given here. And if you look at the graph also, as far as the HFE is concerned, as far as the gain is concerned, what we find here, the current gain at about 1 milliampere of collector current, we find the gain is nearly little above 100. These are the parameters that we will be taking into consideration for the designing of the biasing for the transistor. Now let us look at a circuit using the transistor 2N3904, and the biasing arrangement has been given with this kind of arrangement, where we have deliberately taken a 22K variable resistor in series with a 56K as far as the positive side is concerned, and for the negative side we have a 10K variable resistor and a 10K fixed resistor. The objective of using this variable resistor is to see as to what is the optimum biasing required for getting the best output as far as the input is concerned. For the input we have taken 1 kilohertz at 10 millivolts, that is 1 kilohertz sine wave with a coupling capacitor so that the DC component is avoided and it's only AC which goes there. And then we have the other arrangements, like we have one emitter resistor here and a coupling capacitor, and a bypass capacitor here for bypassing the AC signal. And then of course there is the load. Typically what we have understood, that for a transistor to operate at its full swing, the ideal condition is that this should be half the voltage of the supply voltage. That's the first condition. That means this should be around 4.5 volt if this supply is 9 volt. So with that consideration we shall proceed, and then we will also have seen from the data sheet that at about 1 milliampere current flowing through this is the best option, and that's how we have taken these values. Once we calculate, perhaps we will be able to understand them much better. Here is the same circuit, of course with some ammeters and voltmeters connected to understand the function of the bias voltage and the load voltage, etc. We also have connected a digital storage oscilloscope, 2 channels. The first channel goes to the input signal and the second channel goes to the output of the collector of the transistor. And if you look at the scale here, this is the input signal and this is the output signal. Obviously it is out of phase by 180 degrees, and the scale that we find here, this is in the range of about 5 millivolt. This is in 5 millivolt, whereas this one is in the range of 0.5 volt or 500 millivolt, roughly 100 times. So this is what is the scale as far as the oscilloscope is concerned, and we will now see the changes. What we have seen here, that this setting, which is about say 10K, of half of it maybe about say 5K, so about say 15K here, and this is 56K plus 22K, which is about 78K. And with that, what we notice, the waveform is fairly good, and the output voltage is about 4.5 volts as we have seen in our data sheet, and the current is nearly about 1 milliampere, and the gain factor is against 0.7, it's 7 microamperes, and this is about nearly 1 milliampere. So it's little above 100 what we have seen in the data sheet, and this is the biasing voltage, and this voltage of course is this voltage minus the junction voltage is this voltage. Junction voltage is to the extent of 0.7 volts, and so that's how this is that voltage, and based on the current we know that this will be the voltage drop, and we subtract that, then we get the voltage drop across the transistor, which is about 3.7 volts. The basic fundamental of what we have understood that it should be around 4.5 volts for the faithful reproduction of the amplification. And now what we will see what changes we can do. Now supposing we change the biasing voltage. Now here we are changing the biasing voltage. You see what is happening, the gain is falling. The more we are going, the gain is falling because it is going towards the gain is falling, and so the optimum gain as we see is at about say 4.5 volts, right? About 4.5 volts is the optimum gain that is good. We can even change this also, where we find this further falls, and the gain increases to certain extent, and after that it doesn't have much of impact on this, and so a resistor from 56K to about say 78K is okay as far as the function of this is concerned, because at this kind of biasing we find only apart from the gain which is changing a little bit, the voltage across this remains same, and gain of course changes as we have seen here. So we will see again, now change the gain. Now if I change the current, now it's about say 10 microamperes, it's about more than 100 it's about 1.5 milliamperes. So this is how the change of the biasing voltage affects the output and the operation of the setup